Hello everyone, I am Dr.VRAO. We have been considering the topic of titration of acids and bases and pH of a mixture of acids and bases. That is, in the lecture 26, we had gone through the concept overview of titration and terminology of titration, that is titrant, analyte, equivalence point, end point, indicators, theories of indicators, that is Ostwald theory and quinonoid theory. In this video, we are going to do some problems on the concept of titration of acids and bases and pH of a mixture of acids and bases. And I already told you that in the last video, that is in the lecture 26, I already told you that when we are adding titrant to analyte, I hope you all know the concept of titrant and analyte and the terminology of titration. Okay, and I told you in the lecture 26 that when we are adding titrant from burette to analyte in the conical flask, the resulting solution undergoes pH change. I repeat, when we are adding titrant from burette to analyte in the conical flask, the resulting solution undergoes pH change. And our objective in this video is that calculation of pH of mixture of acids and calculation of pH of the resulting solution when the titration is going on, right? We shall understand the concept by doing some problems, okay, by doing some problems on the pH calculation of resulting solution when the titration is going on, right? Okay. Problem is, calculate the pH of the solutions when the following conditions are provided. When the following conditions are provided. Condition 1, when 20 ml of m/10 acetic acid, that is decimolar acetic acid solution is titrated with m/10 solution of sodium hydroxide, that is decimolar solution of sodium hydroxide. Okay, one thing that you should keep in your mind is that when the titration is going on, there should be equimolar concentrations of titrant and analyte. Concentrations of the titrant and analyte should be equimolar, right? So here they also gave that equimolar concentrations of analyte and titrant. Here, when the 20 ml of m/10 acetic acid solution is titrated with, that is, what is this? m/10 acetic acid is titrated with, that is m/10 acetic acid is analyte. m/10 acetic acid is analyte, that is, we can take in that conical flask, and with the m/10 solution of NaOH, that is decimolar solution of sodium hydroxide. Okay, so now calculate the pH when case 1 calculate the pH in case 1, that is no titration is carried out, that is case 1 is no titration is carried out, that is this is the burette, okay, and this is the conical flask, okay, and in this conical flask ambiton acetic acid is there, 20 ml of acetic acid is there, that is 20 ml of acetic acid is there in conical flask, and NaOH is to be added from burette, that is NaOH is titrant, right. But calculate the pH when no titration is carried out, that is we are that is there is no addition of NaOH to acetic acid. So, there is no addition of NaOH to acetic acid. So, in the conical flask only acetic acid is there. So, in such case calculate the pH. So, acetic acid is a weak acid, acetic acid is a weak acid, and we have a formula to calculate the pH of weak acid, that is pH of weak acid. We can calculate the pH of weak acid by using the formula of pKa minus of log C, of log C, and Ka value of acetic acid is Ka value of acetic acid is 4.74, and Ka of acetic acid, Ka of acetic acid is 4.74. 4.74. So, this is the formula by which we can calculate the pH of weak acid. Usually the formula for calculating the pH is negative logarithm of concentration of H plus ions, that is strong acids, that for strong acids, okay. But for weak acids, but because weak acids undergoes partial ionization, incomplete ionization, that for weak for weak acids we have to consider the degree of dissociation. So, yeah, already I had discussed this concept in the earlier videos, okay. So, pH of the weak acid can be calculated by using the formula half pKa minus half log C, right. So, pH is equal to 1 by 2 pKa, that is 4.74 minus 1 by 2 log C. So, log C, the concentration of acid is 1 by 10, that is decimolar, that we can write 10 inverse, we can write 10 inverse. So, 4.74, this is 2.37, 2.7, okay, 2.37 minus if you bring this minus 1 before this, that becomes 1 by 2 log 10, okay. So, log 10 is 1 and 1 by 2 is 0.5, 2.37 plus 0.5, that is 2.87. So, pH of the solution is 2.87 when no titration is carried out. This is the case 1. Okay. Case 2 is when 16 ml of NaOH is added, when 16 ml of NaOH is added, that is 16 ml of NaOH added to the 20 ml of acetic acid. In such case, we should calculate the millimoles of acetic acid and millimoles of NaOH to know the how much and to what extent they reacted. To know the what extent they reacted, we should calculate the millimoles of NaOH and millimoles of acetic acid. So, millimoles of acetic acid, we can calculate the millimoles of acetic acid by multiplying the concentration, that is 0.1 into its volume in ml, that is 20, it is 2, and millimoles of NaOH can be calculated by multiplying its concentration, its molarity into volume in ml. So this is 1.6. So millimoles, 2 millimoles of acetic acid reacts with 1.6 millimoles of NaOH to form 1.6 millimoles of NaOH, then 1.6 millimoles of acetic acid is reacted, remaining acetic acid is left behind. Okay, so 1.6 millimoles of NaOH reacts with 2 minus 1.6 millimoles of acetic acid. Okay, that is 1.6 millimoles of acetic acid to form 1.6 millimoles of CH3COONA, sodium acetate. It is a salt. It is a salt, right? So how many millimoles of acetic acid is left behind? 1.6 millimoles of NaOH reacted with 1.6 millimoles of acetic acid. But so how millimoles of acetic acid left behind? Acetic acid left is 2 minus 1.6, that is 0.4 millimoles. 0.4 millimoles of acetic acid is left behind in the conical flask. Unreacted acetic acid is 0.4 moles. And what is the compound that is formed in this titration? By adding 16 ml of NaOH, there is a formation of 1.6 millimoles of sodium acetate. What is left behind? Acetic acid is behind. Form a salt is formed. Then calculate the pH. In such case, for calculating the pH, we have to use the acidic buffer formula, because there is a formation of salt and acid is left behind. Then we use the formula acidic buffer formula, that is pH is equal to pKa plus log concentration of salt by log concentration of acid. To calculate the pH, we have to know the concentration of salt and concentration of acid. How can we calculate the concentration of salt? Concentration of salt is equal to millimoles of salt by total volume. Total volume, what is the total volume? This is 20 ml and 16 ml is added, that is 36 ml. The final volume is 36. So 1.6 by 36 gives the concentration of salt. And concentration of acid. So concentration, how many millimoles of acid is left behind? 0.4 millimoles of acid is left behind, that is 0.4 by total millimoles, that is total volume, that is 36. Now we can calculate the pH. pH is equal to pKa 4.74 plus log concentration of salt. Concentration of salt is 1.6 by 36 by acid. Then we can revert this fraction, that is 36 by 0.4. 36 get cancelled. 4.74 by log 1.6 by 0.4, that is 4.74 plus log 16 log 4, and 4.74 plus log 4 is 0.66, that is 4.74 0.66 10 1 okay 5.40. pH is 5.40. Okay, and case 3, when 20 ml of NaOH is added, that is NaOH volume is 20 ml and 20 ml of NaOH is added to 20 ml of acetic acid. Okay. So, when we are adding titrant to analyte, pH of the resulting solution undergoes change, and there is no particular certain formula to calculate the pH of the resulting solution, because from time to time when we are adding titrant to analyte, conditions are varied, conditions varies. Sometimes acetic buffer is formed, sometimes salt is formed, right, sometimes acetic acid remains when no titration is carried out. So, these are the different conditions. Here the condition is when 20 ml of NaOH is added. So, that is 20 ml of NaOH is reacted with 20 ml of acetic acid. So, you have to calculate the millimoles of acid and millimoles of base, because to know the extent of reaction that has undergone, right. So, millimoles of NaOH is equal to its concentration into volume in ml, that is 2 millimoles, and millimoles of acetic acid, its concentration, its molarity into volume in ml, so 2 millimoles. So, 2 millimoles of NaOH reacts with 2 millimoles of acetic acid to form 2 millimoles of sodium acetate, CH3COO, sodium acetate. There is no acid is left behind, there is no base is left behind. So, a complete acid reacts with complete base, total acid is reacted with total volume of acid is reacted with total volume of base, that is acid base are completely neutralized, that is salt formation takes place, which results salt formation takes place, right. So, in this condition we have to calculate the pH by using the salt hydrolysis formula. Okay. Here the acid is weak acid and base is strong base. So, the resulting solution nature is basic in nature. Okay. The resulting solution nature is basic. Okay. So, the resulting solution is basic in nature, right. So, we have to calculate the salt hydrolysis formula. So, base is strong base, so pH is more than 7. So, pH of the resulting solution is because base is strong. So, in the combination of strong base weak acid, the resulting solution nature is ascribed by the whichever is strong in the combination. Whatever is the what is strong in this combination, sodium hydroxide is strong, base is strong. So, that strongness is ascribed to resulting solution. So, resulting solution pH is more than 7. So, when pH is more than 7, then then formula for calculating the pH is 7 plus 1 by 2 pKa plus 1 by 2 log C, where C is the concentration of salt. So, where C is the concentration of the product. So, 2 millimoles of acetic acid. So, concentration of salt is can be determined by millimoles of salt by total volume. So, 20 ml plus 20 ml 40 ml, okay, that is 40 ml. So, it is 0.0005, that is the concentration of salt is 0.05. So, 0.05 can be written as 5 into 10 power minus 2, 5 into 10 power minus 2. So, we can write 7 plus pKa. What is the value of pKa? 4.74 by 2 plus 1 by 2 log C, that is 5 into 10 power minus 2. In the next step 7 plus this 2.37 plus 1 by 2 log 5 plus 1 by 2 log 10 power minus 2. Okay. So, okay. In the next step 7 plus 2.37, that is 9.37 plus log 5 whose value is 0.7 by 2 plus when we take negative sign, that is 10 power minus 2 before the logarithm, that is minus 2, that is minus 2 by 2 log 10, that is 9.37 plus 0.74 by 2 minus 2 by 2 1, that is log 10 1, okay, which comes out to be 9.37 plus 0.7 by 2, that which comes out to be 8.72, that is which comes out to be 8.72. So, pH of the resulting solution is 8.72. Okay. And the case 4 is when 30 ml of NaOH is added, that is 30 ml of NaOH is added to 20 ml of acetic acid, that is amount of titrant is more than the volume of analyte. Okay. So, volume of titrant is greater than volume of analyte. In this case also we have to calculate the millimoles, because to know the to what extent that reaction has undergone. Okay, that reaction is undergone, right. Okay. So, millimoles of NaOH, millimoles of NaOH is its constant, its molarity into volume, that is volume, how much volume, that is 30, that is volume millimoles of NaOH is 3, and millimoles of acetic acid is CH3COOH is its molarity into its volume, that is 2. So, 2 millimoles of acetic acid reacts with only 2 millimoles of NaOH, but millimoles of NaOH is 3 millimoles. So, 1 millimole of NaOH is left behind in the resulting solution. Okay. So, 1 millimole of acetic acid is unreacted, right. So, NaOH, millimoles of NaOH left is equal to 3 minus 2, that is 1, that is 1. We can calculate the concentration of NaOH, that is concentration of OH minus by dividing the millimoles left behind by total volume, that is total volume is 50, total volume is 50. I can write this 0.000, that is 0.02, okay, 0.0, right, 0.02. So, we can write 2 into 10 power minus 2, 2 into 10 power minus 2, okay. So, concentration of OH minus is 2 into 10 power minus 2. If we know the concentration of OH minus, then we are able to calculate the POH, but what they ask to calculate, they ask to calculate the pH. So, now let us calculate the POH, then we can calculate the pH from POH. So, POH is negative logarithm of concentration of OH minus ions. Negative logarithm of concentration of OH minus anta 2 into 10 power minus 2. 2 into 10 power minus 2. It is in the form of x into 10 power minus y. Okay. Then POH is equal to y minus 2 minus log 2. Log 2, that is 2 minus log 2, this is 0.3, that is 1.7. pOH is 1.7, pOH is 1.7, from which we can calculate the pH. So, pH is equal to 14 minus 1.7, that is 13 point, that is 12 point, 12 point, which comes out to be 14 minus 1.7, which comes out to be 12.3, which comes out to be 12.3. So, in this way we can calculate the pH when the volume of titrant is more. Okay. And the next problem is that is problem B. Calculate the pH of the solutions when the following conditions are provided. Case 1 is when 10 ml of m by 10 H2SO4 solution is titrated with m by 10 solution of NH4OH. So, this is the case with a strong acid versus a weak base, but the earlier case is a weak acid strong base, but this is the different case. This is the case with strong acid versus weak base. Okay. So, in this 10 ml of m by 10 H2SO4 decimolar H2SO4 solution is titrated with that is m by 10 H2SO4 solution is analyte, that is m by 10 H2SO4 solution 10 ml of H2SO4 solution is titrated with m by 10 solution of NH4OH. So, NH4OH. Case 1 is case 1 when no titration is carried out. Case 1 is when no titration is carried out. No titration is carried out. Okay. When no titration is carried out. So, when no titration is carried out, that is no volume of NH4OH is added to H2SO4 solution, that is titrant is not added to analyte. So, the analyte solution remains as analyte solution, there is no resulting solution. Resulting solution comes after when we add titrant to analyte. So, the analyte solution is remains as taken, right, as in the initial state, that is no titration is carried out. So, no titration is carried out in the analyte solution, and that is in the conical flask acid is only there, acid is only there, and that acid is strong acid, but in the earlier problem acid is a weak acid, but acid is strong acid. How can we calculate the pH of strong acid? We can calculate the pH of strong acid by the formula pH is equal to negative logarithm of concentration of H plus ions. And what is the concentration of H plus ions? Okay, and already I told you in the previous videos that concentration of H plus ion should be expressed in normalities when we consist with pH calculations. Okay, that concentration should be in normality. Concentration of H plus is okay. So, molarity into n factor, molarity into n factor, because we know the molarity of H2SO4 solution, that is 0.1 molar, that is 0.1 molar, and n factor for H2SO4 it is a dibasic acid, that is 2. So, concentration of H plus ions is 0.2, and it can write as 2 into 10 power minus 1, 2 into 10 power minus 1. So, pH is equal to, it is in the form of y into 10 power x into 10 power minus 5, then we can write the formula 1 minus log 2, 1 minus log 2, that is 1 minus log 2 is 0.3, that is 0.7. So, pH of the solution is 0.7. This is the solution where no titration is carried out. When no titration is carried out, H2SO4 remains as H2SO4. There is no resulting solution, right? Okay. And the case 2 is when 10 ml NH4OH is added, that is 10 ml of NH4OH is added. In this case, we should calculate the millimoles of NaOH and milli equivalents of H2SO4, because milli equivalents and millimoles are equal for NH4OH, because it is monobasic acid, monoestic base, right? So, millimoles of why should we calculate the millimoles? Because to know the what extent of reaction is going on or what extent of reaction that has undergone, right. So, millimoles of NH4OH is equal to its molarity. What is the molarity of NH4OH is 0.1 into its volume in ml. Its volume is 10 ml. So, its millimoles is 1 millimole. Okay, millimole of NH4OH is equal to milli equivalent of NH4OH, because that is only one OH, that is acidity is 1. Okay, but in case of in case of H2SO4, we have to calculate the milli equivalents, because millimoles is different from milli equivalents of H2. For H2SO4, millimoles and milli equivalents are different. So, milli equivalents of NH4OH, H2SO4 is its molarity. What is the molarity? 0.1 into n factor, because milli equivalents is, we can get the milli equivalents by multiplying the normality into volume in ml. Okay. So, this is molarity, we can get the normality by multiplying the n factor, and its volume is 10 ml. So, it is 2. So, 1 millimole of NH4OH reacted with only 1 milli equivalent of H2SO4. That is the basic principle. Okay. 1 millimole of analyte is 1 millimole of titrant is reacted with 1 milli equivalent of analyte, right. So, in such way 1 milli equivalent of H2SO4 is left behind. So, milli equivalents of H2SO4 left behind is 2 minus 1, that is 1, that is 2 minus 1, 1. So, milli equivalents of H2SO4 is 1. How can we calculate the concentration of H plus ions? We can calculate the concentration of H plus ions by 1 milli equivalents by total volume. Total volume is 10 plus 10, 20, 1 by 20. 1 by 20 we can get the 0.10, 0.05. So, 1 by 20, that gives 0.05. We can write it as 5 into 10 power minus 2. 5 into 10 power minus 2. So, concentration of H plus ions is equal to 5 into 10 power minus 2. We can get the pH, 2 minus log 5. 2 minus log 5 is 0.7. Log 5 is 0.69, and we can write it as 0.7, and which comes out to be 1.3. So, pH of the resulting solution is 1.3. And the case 3 is when 20 ml of NH4OH is added, that is 20 ml of NH4OH is added to the 10 ml of H2SO4 solution. 10 ml of H2SO4 is analyte, and we should calculate the millimoles or milli equivalents, because to know the what extent of reaction that has undergone. Okay. So, millimoles are milli equivalents of NH4OH is its molarity into volume in ml, that is 2, that is 2, and milli equivalents of H2SO4, that is its molarity into n factor into volume, that is 10, that is 2. In this case, milli equivalents of ammonium hydroxide and milli equivalents of H2SO4 are equal. So, what forms? That results salt. Okay, complete neutralization takes place. So, this is base and this is acid, complete neutralization takes place, that results salt. So, 2 millimoles of 2 milli equivalents of NH4 reacted with, or 2 milli equivalents of analyte reacted with 2 milli equivalents of H2SO4 to form 2 milli equivalents of salt. So, concentration of the salt is and millimoles of salt, milli equivalents of salt is equal to 2, and concentration of salt is its milli equivalents by total volume. Total volume is 20 plus 10, 30. So, 20 plus 10, 30, which is okay, which comes out to be 0.06, like that, which comes out to be 0.06, 0.06, which comes out to be approximately 0.06. We can write it as 6 into 10 power minus 2. So, concentration of salt, whenever, already I told you, whenever the salt is formed and then you should consider the which is strong in this combination, which is strong. What is the strong? Which is strong? Acid is strong. So, we should use the formula salt hydrolysis formula, that is in this combination whichever is strong, that is a strong acid, weak base. So, strong acid, weak base, that is pH is less than 7, pH is less than 7, pH is less than 7. So, that less than pH formula is 7 minus half pKb minus half log C, So, C is the concentration of the salt formed and pKb value. So, we 1 minute. Okay. So, pH is 7 minus half pKb minus half log C. So, I could not provide the pKb value earlier, but now I provide the pKb value of ammonium hydroxide. So, that is 7 minus pKb is 4.76 by 2 minus half log C. C is 6 into 10 power minus 2. Okay. So, 7 minus 2.38 minus 1 by 2 log 6 plus 1 by 2 log 10, 1 by 2 log 10, which is 7 minus 2.38 minus log 6, whose value is log 6, 1 by 2 log 6 plus this is log 10 1, okay, which comes out to be this calculation, which comes out to be 5.24, which comes out to be 5.24. So, pH of the resulting solution is 5.24. Okay. and the case 4 is when 40 ml of NH4OH is added, 40 ml of NH4OH is added. In this case also we have to calculate the millimoles of NH4OH. Millimoles of NH4OH is its concentration 0.1 into 40, that is 4, right, and millimoles or milliequivalents of H2SO4 is 0.1 into 2 into 10, that is 2. So, here the millimoles are millimoles of base NH4OH is greater than millimoles of or milliequivalents of H2SO4, that is which is 4 and this is 2. In this case basic buffer is formed. In this case basic buffer is formed. So, what is the formula for basic buffer? POH is equal to pKb plus log concentration of salt by log concentration of a base. Okay. So, we can get the concentration of salt. Concentration of salt is 2 milliequivalents of analyte. It reacts with 2 milliequivalents of NH4OH only. So, NH4OH left millimoles of NH4OH left behind is 4 minus 2, 2. So, 2 milliequivalents or 2 millimoles of NH4OH is left behind and salt is formed, 2 millimoles of salt is formed. So, concentration of salt is pKb is 4.76 and log concentration of salt is millimoles of salt formed by total volume, that is total volume is 50 ml and concentration of base is millimoles left behind by total volume 2 by 50. This is cancelled and this is 1 and log 1 is 0, that is POH is 4.76. But what they asked to calculate? They asked to calculate the pH. So, pH is equal to 14 minus POH. So, 14 minus 4.76 which comes out to be 9.24, which comes out to be 9.24. So, pH of the resulting solution is 9.24. So, we have different cases, strong acid, weak base. Okay, if you take the strong acid, in this case we take the strong acid as analyte and weak base as titrant. We can revert this situation. We can revert this situation. Strong acid as titrant and weak base is analyte. Okay, we can revert this condition and we can do more problems. Okay, na? In this way we can solve the problems for strong acid, strong base, weak acid, strong base, strong acid, weak base. Okay. So, I hope you all understand these problems and these problems enables you to solve more problems. Thank you. Thank you for watching.